Okay, so in this lesson we're going to do a problem, and we're going to consider a sphere of radius r which carries a polarization equal to kr. And here k is a constant and r is a vector from the center. So we're going to do two things. The first is we're going to determine what the bound charges are. So this is sigma b, which is the surface bound charge, and rho b, which is the volume bound charge. And then we're going to go on to calculate the field inside and outside the sphere. So first of all, let's look at the surface bound charge. What we previously saw is the surface bound charge, sigma b, is equal to the polarization by our unit vector, which is n hat. Now in this situation, the unit vector is in the r hat direction, okay, so it's pointing really outwards. So what we have is kr dot r hat, and this is at the surface, so it's for when r is equal to big R, and what we obtained is the surface bound charge is equal to k times r. Now if I was to put some units in here, what we would have is coulomb per meter squared. For the volume bound charges, what we have is rho b is equal to minus the divergence of our polarization. And again, all we have to do is consider the r hat term. Okay, so what we will have is minus 1 over r squared by the derivative of r squared by kr with respect to r. And when we work this derivative out, what we're going to get is minus, we have an r cubed inside, so we're going to have 3r squared. The r squared is going to cancel, so we have a minus k, minus 3k. And if we were to put units in here for the volume bound charges, we'd have coulombs per meter cubed. Okay, so that's the first part of this question complete. There's our surface bound charges, and here are our volume bound charges. Okay, so the next thing we're going to do is calculate the field inside and outside the sphere. The previous solution got to our surface bound charge was equal to k times r, and we found that our volume bound charge, rho, was equal to minus 3k. I'm going to calculate the fields inside and outside. So starting with inside, we have r is less than big R. And what we're going to do is go back to Gauss's law. So we have our integral of E dot dA will equal to the electric field by 4 pi r squared. And this is going to equal to the total charge enclosed divided by epsilon naught. Now what is this total charge enclosed? Well, what we can write as a total charge enclosed is just equal to our volume integral of the volume charge density, so rho d tau. So now what this gives us for inside is the electric field dot 4 pi r squared will equal to the volume, so it's 4 pi r cubed divided by 3 epsilon naught by rho. So therefore our electric field will just equal rho r divided by 3 epsilon naught, and it's in the r hat direction. Okay, so there is our electric field for inside the sphere. Okay, of course we could take it a little bit further, so that what we would get and substitute for rho is our electric field will be equal to, for rho it's minus 3k, so we would have minus k r divided by epsilon naught r hat. Okay, so that's for inside. What about outside, where r is going to be greater than the radius? Well, what we must do is look at what the total charge is, and the total charge contribution total is going to be equal to what's on the surface and also what's in the volume. So for the surface, what we have is our k times r multiplied by the surface here, so it's 4 pi r squared, plus the contribution from the volume, so we have plus minus 3k is over the volume, so it's 4 over 3 pi r cubed. Okay, so when we work this out, what we find is we get 4 pi r cubed minus 4 pi r cubed, which is going to equal to 0. So what this implies then is that our electric field outside is going to be equal to 0. Okay, so essentially what has happened here is the surface bound charges and the volume bound charges have cancelled. So then our total charge, which is going to be enclosed by our Gaussian surface outside of the sphere, is going to equal to 0.